What's up, everyone? I'm back with what should be the final video in the series on this HP 8557A and the 182T display. As you can see, it's all covers are back on. It's back. The plug-in is back in place. No extender cable. This guy is finished. And so I thought it'd be cool to just wrap this one up by using it for what I bought it for, which is to calibrate some of my test equipment, and which is what I'm doing now. And so I thought it'd be cool to just show it in action with a couple of pieces of test equipment that I need it for, and starting with this 8654A, this signal generator. And I did a video on repairing the range knob for it, and you could see that for some of the ranges, the sine wave didn't look all that pretty, and also it's a bit inaccurate, and you can kind of see that there. We're set dead center at 50 megahertz, and we're at 51.6 here, so yeah, it needs some work. And so I thought we start with this one. Not going to show the whole calibration of this 8654A, just the parts that require the spectrum analyzer, and then maybe we can fit in one more. I have an SG 502, I think it is, the sine wave, leveled sine wave generator for the Tektronix plugin that we can do as well, that I think I'd need this for. So anyway, let's give this a whirl. Alright, so this is basically the setup. I've already started with checking the voltages on the 8654A. They're bang on. They didn't require any adjustment. The 20 volt rail and the negative 10 volt rail. And so the next step is adjusting the detector bias and AM distortion adjustment. And so detector bias adjustment is it's adjusted so that the RF output voltage is tracking with the veneer adjustment, so that for the full range of that veneer. And so that is what there is a detector bias adjustment or trimmer pot that is in this assembly, which is why you need to remove it out of the unit. It's a bit of a pain, and it's on the back side of it, and you're going to be, the way that this is set up, this is all in the service manual. So the input to the attenuator, which sits here, this is the attenuator knob. You're taking that input from this assembly and putting it through a 10 dB step attenuator, and that is going to the input of our spectrum analyzer. So that is the setup for the first portion of this step, which is adjusting the detector bias. And so for the first step, we're adjusting the veneer so that, and unfortunately, well, let's actually, we can get this in the shot too. If I just also have our voltmeter connected up to test point number 2 on the backboard there, to monitor the veneer voltage, and it needs to be set at 2 volts. We're setting the output level to 10 dB, and then adjusting the veneer so that you get 2 volts on the voltmeter. And so also, once that is done, oh, and then of course you want your step attenuator to be at 20 dB for this. And then you're going to make some adjustments, 40 dB step input attenuation as well. You're going to adjust the reference level to bring this up to the um, fifth division, vertical division from baseline, or 3 below the top gradical line. And this thing is drifting a little bit, so we've got to make adjustments here and there. At the reference level, fine. Okay. All right. And so this is for the first step. Now, to check the range of the veneer, we need to go to bring this down from 10 to 0 dB on the output level. And then we're going to adjust our veneer so that the voltage is reading -2, I'm sorry, 0.2. No, I was right, -0.2. So you start at -2 volts and then you go to -0.2 volts. Okay. And of course you can't see this on, I'll show you guys again on the digital multimeter. Oh, we went too far. This one's a bit more difficult to dial in. All right, there we go. And so now we've adjusted the veneer so that we are reading negative. That says 200 millivolts because it's auto ranging, but that's same thing. Okay, and then we bring our step attenuator to 0 dB, and you can see we are now still at the fifth gradical line, vertical gradical line. I've already made the adjustment. It did require some adjustment. Wasn't off too much, but that's basically what you're doing. And then you're going to go back and forth. So if we go back to 10 and bring that up to -2 volts again. It needs a little bit of an adjustment. That's basically it, right? Okay. So actually I can show you. See, we're basically right back up at -2 volts. So that's the detector bias adjustment. All right. So we're seeing a straight line here because our frequency span is set to 0. So we are really, our span is very tight. And, for example, if we come out a little bit, now you can see that the peak, as we widen that span, it gets smaller, right? And so that's just so you can make this adjustment, okay? The resolution bandwidth is at 300 kilohertz. So this step is good. So let's get set up for the next step, which is the AM distortion adjustment. Okay, so we may have a problem. I'm not 100% sure, but for the next step, the AM distortion adjustment, if we look here, it says to make sure, so we look at step number 8, before repeating, it says to set the signal generator's output level to plus 10 dB and adjust the veneer to give a voltmeter reading of -2, right? And so we've done that, and we're back, right? So we're at the fifth gradical line, 20 dB for this step attenuator, -2 volts for test point number 2 on the A3 board. And so then, moving on to the signal generator, the modulation level, set the modulation level control so that the upper peak of the sine wave is at the 8th division from the bottom, so basically the top gradical line, and adjust the distortion adjust pot so that the lower peak of the sine wave is at the 2nd division from the bottom. So if we look here, this is the modulation level. Look what happens. So we're going to bring this to the top and it clips. And we can get to this no problem, but we're clipping here, which is interesting. So, not too sure what that's about. Okay, so that was definitely not clear. So it looks like we needed to bring the output level down. That's why it was clipping. So from 10 dB to 0, because it almost looks like the way that they word this um, to sorry that it's a little bit blurry here. Let me see if I can. There you go. Before repeating step 6. Yeah, okay, that was my fault. I was reading it here as if they were setting you up for the next step to adjust the output level back to 10 dB and adjust the veneer to -2. So I made a mistake. It should be, this is where you should have it set 0 dB, and then the voltmeter should be, the veneer should be adjusted so that the voltmeter is at -0.2 volts to make the distortion adjustment, because now we got this is exactly what we want to see. And if I adjust the distortion adjust pot, it does make a difference. You can see it right there. So that looks good, right? Yep, cool. Okay. All right, so then at the final step, it then asks you to it then asks you to bring it back down to fully, bring the modulation level all the way down fully counterclockwise, and it should not have adjusted the reference level that at the fifth gradical line should not have moved by 0.02 divisions, and it hasn't. So that wraps up the AM distortion adjust and detector bias using the 8557A. Alright, so this is the frequency and range adjustment. Now, in the manual for this guy, there is no specification of using a spectrum analyzer. It's just using a frequency counter. But I've actually tied in the spectrum analyzer. I've kept it in place, just added it via this T. And because I did want to see, I know for a fact when we were looking at this unit before, some of those sine waves just didn't look very good. They looked misshapen, not very symmetrical, and I thought it'd be interesting to look at how how they looked with the spectrum analyzer hooked up. Now, one thing that's interesting is I swear this thing looked a lot less accurate as far as the frequency, but we're at 50 still, and hooked up to our counter we're at 50.4, which is within spec, at least for the 50 megahertz reading, 49.5 to 50.5. So that's good. Let's take a look at these other levels as well, see if we find any out of spec. Yeah, so for this range, everything is within spec, but you know, if we look at the spectrum analyzer, you can see here we're at 20 megahertz per division for the span, and so this is our primary peak, and then you can actually see the second harmonic for this guy right there. That little peak right there, that's about 35 megahertz away from the main peak, and this is just the LO feed-through peak. Yeah, that's pretty cool. All right, so we've actually been able to improve the accuracy for the frequency at 50 megahertz by adjusting the inductors in this wheel. So this is not the inductor for the 35 to 66 megahertz range, but it's actually that inductor isn't accessible because it's currently You can just about see it. Maybe not. Well, it's blocked anyway because it's literally making contact with the oscillator assembly board over there, right? So in order to make an adjustment, you need to pull the wheel back so that you can access that trimmer inductor that and make an adjustment and then put it back and then check if it's made it better or worse. And that's basically what we had to do. And so now we're within spec, which it's calling for. It should be plus or minus 50 plus or minus 0.01. So we've done that. And then we're going to be doing that for each range. So we've done the 35 to 66, and now we'll do 66 to 130, which I believe, if I'm not mistaken, was 66 to 130 or 130 to 250 that was really had that asymmetrical sine wave. So I'm curious to see how this looks next. Okay, so to check these other settings, these other ranges, basically you're going to go through the range and do not make any adjustment at the range variable capacitor. Okay, so it just stays there, and that should be where, so for example, by going from 50, the 50 set point on the variable capacitor for this range, 35 to 66, is 97.8 for the next range, 66 to 130, right? And so we should be looking at a frequency anywhere between 97.8 and 98.0, and we are at 98.6. And also what's interesting is look at the size of that second order harmonic for the for the main peak. It's a lot larger than what we were seeing before. So this could be the range that was looking a bit asymmetrical. Yeah, so we did bring it into range, so it's below 90. It's between 97.8 and 98.0, but still see that second harmonic. It's a much larger peak than we saw for the harmonic for the 50 megahertz signal, and if we go to full span, you can also see the third harmonic here too. All right, and we're back at the psychedelic scope. Yeah, so this is I just wanted to look at the sine wave, see how it looks visually, and I don't know. I guess it looks better. Maybe this isn't the channel that I was thinking of, 'cause that looks pretty good. But still, you can see that's those second and third harmonics. They look much more prominent than for the 50 megahertz signal in the other range. So let's keep going. All right, so not all of these have a adjustable inductor. So for example, for the ranges of 130 to 250, it's a little bit different for L5 and L6. So for example, for L5, we're at a little out at 194, but it was at over 196. And so basically, for this step, it says to reduce the loop areas equally by pinching both loops in, right? And that's a little, not quite sure what they mean there, but you can kind of see these little loops. So I just sort of, I guess, I just brought them a little bit out, or tried to widen that. You can kind of see, I guess, where they mean pinched in. So I just tried to widen them a little bit, and that seemed to bring it way down. So this is the highest range, 250 to 520. It says you can adjust that by adding equal amounts of solder to those two areas, right? The two slots, okay? And what's weird is that the range is specified as 38.4 to 35, 384.4 to 385.2, but that doesn't match up with where the needle sits. Let me show you. So that's where the needle sits, almost right at 370, if I'm looking at this correctly, right? 310, 320, 330, 340, 350. So, you know, I don't know. It just seems a bit weird because all the other ones are matching up very nicely. And maybe that's a mistake, transcription error, I don't know what. We're at 373, which seems better for what, you know, where the needle. I'm not going to mess with that. But then there's one more. Or one more that was out, and that's 18.6 to 35. Let me show you that one. So for 18.6 to 35 megahertz, it should be at 26.7 to 26.8. This is the best I could get it. And the reason for that, I think, is because the windings on around the inductor had actually, you can see that there's a bit of an adhesive that keeps them in place. Well, that they had become free of that adhesive, and so my quick fix was just some electrical tape to hold them in place, and that made it a lot better because it was well above 27, and I couldn't, regardless of what adjustment I made, I couldn't get it any closer. That's the best I could get it, a little under 27, and I think I'm okay with that. Okay, so we've got the RF assembly back in the unit, and I gotta say, it's already looking, you know, a lot more accurate. Right, so we're at 30 here, and it's reading roughly 30.1, 30.2 there. And again, it's not going to be perfect, but if I believe the specs are actually pretty wide, I think it's like plus or minus 0.5 for at least one of these ranges, and we're there. I think it's actually this range. So over here to 35. So for example, at 60, we're reading. Yeah, it's not going to be for all the ranges. It's probably a percentage. There's a percent error for each of these because it's not going to be that accurate for the higher ranges. But for this range from 35 to 65, it was basically plus or minus 0.5 megahertz. And so at 60, look at that. We are bang on, right? 65. Yeah. I mean, this was the one that we were able to dial in the best. So you're going to see that. All right. For this range. But, yeah. Looking good. So that was actually all of the calibration adjustments that the manual calls for. Well, with the exception of one. They do one for basically signal amplitude, which there's really no point in. Well, actually, we did check that in the first video I did on this, a very crude check using an oscilloscope, and it did seem pretty bang on, and actually in my use of the instrument, the amplitude does seem pretty good. So really my concern was the frequency, but you would really need a power meter and a power sensor to do that, which I do have, but the power sensor itself, it's questionable at how accurate it is, so I really don't see the point in doing that. But so yeah, so basically the manual has, we can scroll down to these really quickly. it has a bunch of performance tests you can check. And that's actually what I wanted to do next because of those harmonics that we were seeing. Um, yeah, see, look at this is all the tests that you can do and what the spec should be. And then you have the adjustments, right? So I did do this off camera. Power supply adjustment did not require any adjustments. Detector bias and AM distortion adjustment, we did that. Then there is the meter amplifier adjustment. So this is the one that I'm not going to do because it requires a power sensor. Tuning capacitor pulley adjustment, skipped that because that's really just making sure that you're getting the full range of each range. Didn't seem like there were any problems there, but what we did just finish was the frequency and range adjustment. So that we did just do. And so I'm going to scroll back to the harmonic distortion test, which is what I'd like to wrap up with. If I can find it. Yes. So here you go. 20 dB below carrier. So the harmonic should be 20 dB below the main signal, 25 dB below carrier for 18.6 to 130 megahertz. All right. So that's the spec. And yeah, so it gives these ranges here. This is how we'd set our spectrum analyzer. Now, unfortunately, we're not going to be able to do the largest range because we only have a bandwidth on this thing from 350 megahertz. You need a larger a spectrum analyzer with a bigger bandwidth to do the biggest range. But anyway, we can do most of them. So settings are still the same. Set the signal generator's frequency tune control for the lowest frequency and tune across each band. All right. Let's do this. All right, so this is actually the first band here, and I was trying to just get both instruments in the shot. Starting with the lowest range, so we are basically at 10 megahertz right now. And so we're just going to tune across the entire range. You could see this is the 10 megahertz peak, and then you have the second and third harmonics. But you can see it says we should be 20 dB below the carrier signal, and we are, just about. But if we tune through the entire range, everything looks good, right? So let's do the other ranges. All right, so now we are at 18 to 35, and again, it's the same deal. We have increased our frequency span, so now we are looking at 20 megahertz per division, right? So you can see, if we zoom in a bit over here, this is just the LO feed-through peak, and this is our peak roughly at 18 megahertz, and then we have our second harmonic. You can't see the third harmonic, but again, we're just gonna tune through. And once again, now this spec is a bit greater. We're looking at at least 25 dB below. All right, and so we are at 10 dB per division, so 10, 20, and that looks to be about below 25. We're almost sitting at 30 dB below the carrier. So again, per this instrument, it is matching spec, and it is in spec through the whole range. So that's good. I don't know if I'll do all the ranges on camera unless we find one that is out of spec. Now I did just want to point this out real quick. Look at how, for this is the 35 to 66 megahertz range, and this is what I was initially observing is just look at how little you can just about resolve that the second harmonic, the third harmonic isn't there. So this appears to be the cleanest range. At least it provides the purest looking sine wave of all of the ranges on this instrument. Technically a pure sine wave should have no harmonics, but you know, that would be ideal, which we're not able to achieve. So anyway, I mean, this certainly has the cleanest range. Yeah, I mean, that is just, yeah. So that is the 35 to 65 dB range. Okay, so this is actually the we're actually looking full scale here, but this is the 30 66 to 130 range. This was the range that I started noticing the much larger second harmonic peak. But even still, per the spec of this instrument, we are still 20 dB below the carrier signal. So this is still good per the manual. All right, well, unfortunately, I can't, like I said, I can't do the largest range, but I was able to fit in the second to largest range, 130 to 250, and right now we've got it at about tuned to 170, so that's our carrier signal right here, and then our second harmonic right there, and again, it's within spec for that. So this unit passes the harmonic distortion test for as many of the ranges we can test for. Um, so yeah, and even at the higher ranges, 170, we're even 170.7, plus or minus 1 megahertz at these higher ranges. I'm okay with that. So this guy's looking in much better shape. And we got to try out our spectrum analyzer that I'd been working on for quite some time. So this, I think, has been a successful endeavor. Um, yeah, this is great. So I'm going to finish the assembly here. Um, we can wrap that up. Now, it's too late in the day. I was going to try to fit in a leveled sine wave generator from Tektronix. I probably won't do a video on that because you guys get the picture. But this will allow me to finish some stuff that I've had sitting around for a bit. And I must be a masochist because next on the docket, as far as HP equipment goes, check this guy out. We've got this guy's younger but beefier brother, the 8558B, getting into the microwave range at 1500 megahertz in an 853A mainframe. This could go in a 182T, but this is just what I got it with for 20 bucks. So this guy, it's probably a switch issue again, but fortunately, hopefully that won't be too difficult, because I can use the switches for my other 8557A, which I know are all working. So we don't really have to mess too much with the finger contacts, or at least making ones and whatnot. We already did that. So yeah, that's the next thing that I'm not sure when I'll get to, but that's the next HP piece of equipment that I'd like to work on. And then I'm done with old spectrum analyzers. All right, but yeah, this was a lot of fun. The main purpose of this is this was my first spectrum analyzer, and I wanted to earn it. I wanted to learn more about them, and that's what I thought the purpose of this restoration was. It would, I get to learn how they work, even though it was more of a mechanical issue. It did go down a bit of a rabbit hole. I got to look at the 7-stage log amplifier and how they do the step gain for the reference levels and everything. It's really, really cool. That's why I love these old instruments, because you still get the service manuals for them. But anyway, we're going to leave it there. I hope you guys found this interesting. If you have any feedback, leave it in the comments, and I'll catch you at the next repair.